what is meta-regression? Meta-regression, first of all, can only be really applied if you have more than 10 papers. And meta-regression, what it means is that you have to remember meta-analysis, there are two parts. One is that you are doing a pooling. A pooling is great. Pooling means that you take lots of different papers and you pool them. And then you say, oh, I've got all these papers with standardized mean deviation, or I've got all these papers with relative risk, and I pooled them. I got this amazing number. So I've combined 10 papers. And in those 10 papers, I brought them together and I created a data set of 1,000 patients. And then I had a reduced confidence interval, and I proved that this treatment works or not, doesn't work. And for the last 5 years, they've been struggling and they didn't know. And I am, you know, I am the Iron Man of the Marvel Universe. Yeah, I've done it. You know, I've done this through my, but the problem with this is that have you been actually looking at grapes versus olives? Have you been comparing grapes to grapes, or have you comparing grapes to olives? Because this is the other bit. So the first bit of the model is always going to be something like for relative risk would be something like Mantel Heisel, and for something like a continuous such as a standard mean deviation, you will use some sorry. You're saying something? Oh, somebody was saying. You will use something called various variants, basically hedges. You'll use hedges. So these are your pooling models. But there's also a model we use to calculate heterogeneity. And the heterogeneity model is a little bit different. So heterogeneity model can be something like Paul Mendel. And Paul Mendel, which you can use for relative risk, for example, a binary, basically, which means it's a 0 and 1, for example, will calculate heterogeneity. Now, heterogeneity is bad because heterogeneity means all the papers are different. They are actually grapes and olives, and they are different from each other. But the heterogeneity is also positive. Like diversity is a positive, so difference between papers is positive, because now you can say, well, why are these papers different? And that brings us to something called meta-regression. And this brings us to our original models. So first of all is, you don't need to remember this formula, but I'll just simplify it for you. What we're trying to say is that, first of all, there's fixed effects. Fixed effects means that they all are different from each other in a very specific way. So what happens is that one grape compared to another grape, one grape is bigger, one grape is smaller. Yeah, one grape is black, one grape is green. They vary in very specific ways, but olives are very different. Their composition, consistency, size, shape, everything is very different from a grape if you look at it carefully. Even though initially from we squint and look at it from far away, they look like the same thing, but they're not. So what we do is we use something called a fixed effect model. Fixed effects model says they're all grapes and they all vary each other in a fixed way. Then with the random effects model, which only takes the fixed effects model and said there's some things that are unknowable. Yeah, like the universe is unknowable. Yeah, so the size of the universe, for example. So they say unknown. Yeah, so there's unknown. And then finally, with the meta-regression, what we say there's a third variable, which is that there is another variable which can explain some of the difference between the papers. So now you've got fixed effects, random effects, and you've got a third one. So this is what is called a mixed model. Now we call this a mixed model. So there's fixed effects model, random effects model, which also took in the fixed effects model, and then there's the mixed methods model, which uses all three models. Yeah. So guys, so this, if you go to your book, and this is which page is on the book? This is 821, I think. One second, let me bring this up, because you'll have to do the code here. One second, I'm bringing it up. This is no, it's four. This is a 421. 421 in the book Doing Meta-Analysis with R. To go to 421, and what will happen is that you have to run this code, and then you basically this library tidyverse detmar meta, and then you will run this first code, the data for third wave, and you should be able to see the third wave data set. Yeah. Okay. Let me know if anybody can do it. Okay. Let me know in the chat or whatever. Laura, Nicole, Bharat, Zainab, have you guys been able to do this so far?
I'm just logging in, not yet.
When you guys can do it. Kiara, Harjeet, Celestine, Clement. Any luck?
Not yet.
I'm still.
Oh, yeah, the connection is very slow. It looks like this is what you would see if you do. Yeah,
Clement is trying to load the
very good.
libraries.
So if you do the glimpse, if for somebody, if the code is not working, you need to reinstall all of them. Yeah. And then once you've done this, loaded up library, tidyverse, data. So these are the packages. We loaded them up. And actually it's also got the third wave data set in there. So data third wave. And that loads up the data. And then you go to this and you run the meta-analysis. And then after that we'll go into meta-regression. But you run the analysis. And the output will be mgen from MetaGen. MetaGen is basically used for, this is a standardized mean deviation, and MetaGen will create the output. As you can see, the summary measure is standardized mean deviation. It's a random effects is true to random effects. This is using a REML. Now REML is used for continuous variables for the heterogeneity. Yeah, but this uses a hedges for the continuous model and REML. So there's only two you need to know about. REML, Paul Mendel. Paul Mendel for binary, REML for continuous. And HAKN is the Hartung map adjustments, which are just a slight modification, like a filter on the random effect. You don't need to know much. You all need to know is hedges. This is going to use a hedges, and this is going to use an REML for the heterogeneity. Those are the two models. But we'll go through that in a bit of detail in a minute. Now, if let's see if anybody's got to hear summary mgen, and that is the meta-analysis that you should be able to see. And this is pools all the numbers and gives you the random effects. And it gives you heterogeneity. Heterogeneity is I squared, which is 62%, which is high.
Please, can you go back to the previous screen?
Yeah, this one.
Thank you. Yes.
So you just need to go to the book and cut and paste it. You shouldn't type it. Go to the book. Yeah, it's easier. 4.2.1.
Thank you.
Just go there and cut and paste all of that.
Thank you.
Yeah. All right. Let's see how people are keeping up with this. Let me go back to the. Let's pick on some people. Mahdi, Mahmoud, Safa, Noor. Any luck? Hamza, Justice, Najib, Muhammad. Any luck so far?
Doing it currently.
Doing?
Yes, doing it.
4.2.1. Load the libraries first. Yeah? Libraries first. Okay. Then load the data set. Yeah, 4.2.1. Yeah. And then load the data set and then run this. Then you should get summary.mgen. You should get all of this. Run the code in order. Yeah. And then you should get this meta-analysis. Yeah. Which is inverse variance, which is hedges. Hedges is critical. Yeah. This is the one you use for standardized mean deviation. For binary ones, you generally use a Mantel-Heisel. Okay, so you don't need to know that. It's like a binary answer here. Mantel-Heisel, hedges. Mantel-Heisel, hedges, yeah? Or for the other one, Paul Mendel or REML. Paul Mendel, REML. Depends on whether it's continuous or, binary, yeah? It's not complicated, yeah? It's very, very simple. Okay, so let's see if anybody's gotten to this point yet. Let's torture some people. Vihan.
Yeah, got it.
Salongo, Rami, Monica. Laura is refusing to let me unmute. It's fine. Nicole, Bharat, Zainab, Valerie. Have you got to this point?
Yeah. Thank you.
Very good. Very good.
I
All
think
right.
I'm having issues with my own. It's not going.
It's not. Right, the code is not working.
Yeah.
All right, you need to install all the packages. Sometimes it happens with POSIT. So go to chapter 2, install all the packages, and then do library.
Okay, thank you. I'll do that.
And then it'll work. You can see the heterogeneity is more than, so we convert the heterogeneity to something called I squared. It's actually tau squared is the real number. We convert that to I squared. Anything more than 50% indicates, oh my God, these are now grapes. And so there's a difference, yeah? Just to remind you again, inverse variance, REML, yeah? Hard tongue map, which is filled out. Now, again, to emphasize this again, what estimator should you use? For continuous data, the restricted maximum likelihood estimator is the first. That's quite a mouthful. I don't even can't even remember that usually. And for binary, Paul Mendel. Yeah. Just to emphasize this again, random effects is sorry, fixed effects is saying that there is a fixed difference. Yeah, it's the CK. And random effect says there's an extra difference we do not know, mysterious E. Yeah, a mysterious E. So this is the formula. Again, to emphasize the standardized mean difference or mean difference, we use a Hedges. Hedges is the best model, what's called inverse variance. It's a very, very good model to use. What it does is it basically does give the weighting is the inverse of the heterogeneity. And you don't need to know that, but in essence, it's a very, very good model. Yeah, it uses the variance, yeah, which is the variation. Now we come to Mr. Meta regression. For this, if you guys have all caught up, you need to go to chapter 8. To chapter 8. And in chapter 8, you need to go to 8.2. But let's go over some aspects of this first before I torture you about this. Yeah. So going back to meta regression. What is meta regression? Meta regression means that I have an explanation. Yeah. So I have an explanation for why these papers are different. And people might say, are you crazy? How do you have an explanation? I said, yes, I've got a mathematical model that explains why paper A is different from paper B. And they say, why? Oh, well, I think there are more diabetics in paper 2, 3, and 4. And that's why they have a higher death rate. And he's like, oh my God, you're right. Because you've got a formula, which is this line. And all the papers, you can see the variation in those papers is being explained by this line, this formula. It's amazing. So this is showing that most of the papers are clustered around. So the heterogeneity, the differences are being explained by the fact that there are, for example, more diabetics in one paper. This is amazing. This is perfect. So you've explained the heterogeneity. And this is what in medicine is called causation. Causation would mean something like, oh, you say Down syndrome, people have cushingoid heart defects, for example. Yeah? Causation. But meta regression is great because you can explain the heterogeneity. But going over these formulas one more time just to make your life easier. So library, which is we used meta, dmetar, and tidyverse, and then we just ran this with a basically a hedges, and then REML for heterogeneity, and HAKN, which is hard tongue map, which is just like a filter. You don't have to use it, but it's useful to use. And they gave us this result, which has gone into something called MGen, and this showed a random effects pooled standardized mean deviation 0.57 with a reasonably wide confidence interval, and that the heterogeneity was high, 62.6%, so more than 50%. Yeah. Then again, to emphasize the estimator for the binary Mantel Heisel, for a standardized mean deviation, you basically use a hedges. And then for the heterogeneity, for continuous, use RMLE, and for binary, use Paul Mendel. Yeah, you just have to remember those names. Again, to emphasize fixed effects model and random effects model. The random fixed effects model says, oh, there's just one variation, which is fixed. Random effects model says, no, there's some which is mysterious, E. Yeah, we talked about this. Now we've moved on to the next bit. I don't know if everybody's caught up. 8.2. 8.2. And then what will happen is in the third wave data set, you need to basically cut and paste this code, and it will create this extra variable. Yeah, it will create this variable called year. So you need to run this code, cut and paste the year code, and then let's see what happens. And let's go through the group and see how far everybody's getting by cutting and pasting this variable. Yeah? All right, time to torture some people. Let's start somewhere. Bharat, Madi, Muhammad, Nurane, any luck so far? Noor, Jobran, Aki, Ali, any luck? Guys? Lama, Adrija, Mahmood, Safa, Hamza, any luck? Sorry?
Not yet. Not yet.
Not yet. I'll give you guys a bit of time then.
It's just doing it.
Najib, Muhammad, Krishan, Christelle, Sarah, any luck? All good. Christelle is saying good. Ayodji, Hadi, Rania, Helena, Pratik, Halima, Valerie, any luck?
Yes, all good. All good.
Good.
Okay. Buyant, Monica, Samavita, good.
Yeah, good.
Valerie, Zainab, Nicole, and Monica, any luck?
All good.
Vihan, Solongo, Clement, Celestine, Harjeet, Kiara. Have you guys managed to get this point now?
Yep, all
Yes,
good.
I'm there already.
Yes.
Yeah, all
Very
good.
good. All right.
I
So
did.
now you created the variable. Now you need to run this next bit of code, which is meta regression, meta reg. So you run this code and it will output to m.gen.reg, and this meta reg, and this is meta regression based on year. Yeah. So just cut and paste this code, and you should see. And after this, you just press m.gen.reg, and this will appear. This is amazing. If you guys do this, you will see that the heterogeneity is accounted by the year of publication. This is very interesting because this does happen in medicine quite a bit. That a new technique has come out or whatever, and now you're saying, well, the old technique was crap, but all the old papers are before, and therefore the new technique explains most of heterogeneity. And new technique papers were published recently, for example. So in this case, the heterogeneity, 77% of the heterogeneity is due to this one variable, which is the year of publication, which is amazing. So you've explained most of the heterogeneity straight off. Yeah? Okay, let's see if everybody's caught up. Kiara, Harjeet, Celestine, Clement.
Yep, all done.
Still doing
I'm
okay.
good.
Man.
Yes, I'm okay. I'm on the same page.
Salongo, Vihan, Rami, Monica, Buyant. What's happening in the chat? Nobody asks any questions, okay? Zainab, Valerie, Halima, Pratik,
All
Helena,
good.
so far? Rania, Hadi, Ayodji, Christelle. Have you guys done it? Have you got the meta regression to work?
Can we please go back to the previous slide?
Very good. Okay, fine. So what you do is that this you have to go to you have to cut and paste this from the book. Meta regression with R. Yeah. This is chapter 8.2. 8.2. So you have to create this new variable, which is year. Yeah. So you have to cut and paste
Yeah.
this year
Okay,
code.
it's fine now.
Okay, and then you do meta reg, which is meta regression, and that does mgen, which is the previous code that we outputted from our previous meta-analysis, and then the year, which is the variable. And we saying, is the year account for all the meta regression, all the problems there? And then we run it, and then we type m.gen.reg, and it shows us the meta regression. So it says, well, yes, you are right. That is amazing. 77% of the heterogeneity is accounted by the publication year. Yeah. So 8.2. and you should be able to see it. Yeah. So the law of the heterogeneity is being explained, which is brilliant. Yeah. So let me just go through the group one last time, and then let's see if everybody has caught up. Muhammad, Murad, Jobran, Faith, Lama, Bharat, Maddie, have you guys caught up?
Yes.
Very good.
Yes.
I'm having one issue.
Yeah, yeah.
When I copy and paste the code, when I put in m.gen, it says it's not found. Does that mean I
Oh,
haven't
the
installed
M.gen is
something?
because you have to run the previous. Have you joined late?
No, I had the years put in, and I put in the previous.
No,
I've
it's
got previous
because
outputs.
so what you have to do is because you have to generate m.gen. So you remember this is the third way data set, which is that if you go to chapter 4.2.1, 4.2.1, and then you create the mgen. You have to do this.
I've done those steps.
You've done those steps.
I've done those steps. Yeah, I've got the results of those.
And you've got m.gen.
Mine
Did you
says
get?
m.cont.
Oh no, it should be m.gen. M.gen is where you should be.
Okay, I'll look back through and try and find where I've gone wrong.
Yeah. So basically, it is the mcont is the next one. It's so it should be metagen. So this is Matty is 4.2.1, the pre-calculated data set, and then in that you run the metagen, which outputs to m.gen, and then it will work, and then mgen.
Okay, maybe I put in slightly the wrong thing. I'll go back and try again.
4.2.1, yeah. Okay, and let's torture the others. Nurane, Aki, Ali, Dija, Safa, Hamza, Justice, Najib, Muhammad Kirshan. Yes? Good. Done it? Or no? Crystal?
All
you?
good here.
Okay, very good. Let's move to the next one then. Now, let's do a bubble plot. That's the next one. Bubble.mgen.reg, and then it will show you a bubble plot. What is a bubble plot? Bubble plot basically means that what you're doing is that you're looking at standardized mean difference versus covariate here, and you've created this formula. And if they're all around this line, that means you've explained it apart from some outliers. You've explained why the heterogeneity is occurring. Yeah. So just run this bubble plot, guys. Just run the bubble plot and see if you can produce any bubbles. Celestin, Sumuchku, Muhammad Murad, Muhammad Nahuli, Muhammad Bahasha, Jobran. Any luck so far with the bubble plot?
Yes.
Very good. All right. Jobran, Faith, Lama, Bharat. Then who else is there? Aki, Ali, Adrija. Any luck? Safa, Hamza, Justice.
All good.
All
Very good.
good.
You saw the bubble plot. And you explained it. Najib, Muhammad, Kirshan, Kristal, Ayodji, Hadi. Any luck?
All good, doctor.
Rania, Helena, Pratik, Halima, Valerie, Zainab.
I
Laura?
think it's good.
All good.
Very good, very good. Okay,
Yes,
let's
I'm
move to
ready.
very good. Buyant.
Yes, go.
Uh,
Okay, doctor.
oh, very good. Clement, Harjeet, Kiara.
Yeah, all good.
Very good. All right, fine. So we explained this. Now we can do another one, which is on risk of bias. So we run another bit of code. If you could scroll down in your chapter 8.2, then you can do it on risk of bias. So meta-reg, mgen, risk of bias. Just cut and paste the code, makes your life easy. You have to remember, as I said before, that if you make even the slightest change, which is like an extra space, or you turn into a capital or whatever, it has such huge problems. This is one of the problems with R is that It doesn't require like even the slightest variation. Yeah, it doesn't even like the slightest variation from the code. So if you run this, then you got another heterogeneity plot, and you can see that that is mgen risk of bias, and you can now see that this is only accounting for 15.66% heterogeneity. It's not a lot. Yeah. All righty. Kiara, Harjeet, Clement, Solongo, have you guys managed to run the second bit of code?
Yes.
Vihan,
I did manage.
Yes, thank you.
Monica, Buyant, and Zainab, Valerie. Yes. Success.
Yes.
Halima, Pratik, Helena, Rania, Luck, Hadi, Ayodji, Kristal, Kershon, Muhammad, Najib, Justice.
Yes.
Yeah. All done?
Everything is good.
Very good. All right. So that's the majority of you guys. Now, multiple meta. Oh my God, I'm going to expand your brain now. Multiple meta regression. What is multiple meta regression? Oh no, multiple meta regression means we're just gonna. Last time we cooked soup. Now we're gonna cook a multi-course dinner. Yeah. So what we do is we want to say that we can build a model with more than one. More than one variable. We will build a gigantic Lego set. Yeah. Now the problem with this is something called an overfitted model. An overfitted model is the green one, which means that, oh, I can explain everything. Yeah, I can explain everything. Why the universe is this size, and why everybody likes to eat fried eggs in the morning or whatever. So I've got a fit that will fit everything, but that's not correct. So it's called an overfitted model. The other interesting thing is something called multicollinearity. Multicollinearity basically means that two variables are not independent, actually. They're not independent. So it may be that, for example, like we were discussing before, the risk of bias and the publication year might be correlated, but the recent papers might be of a higher quality. So for multi-regression, there are lots of models, but what we do is we do something called a forced entry model. We've got to force our way in. This is the default setting. We force our way in and we run all the predictors simultaneously. Multi-meta regression. Now, the first thing is with multiple regression is I'm going to do this for a bit of excitement, but in real life, you won't use multi-meta regression that much. Yeah. So we have to use a package called Metaphor, which is the more advanced package. And that's one of the reasons I want to do this, is that you guys know what multi-meta regression is. Once you do it, it's actually quite easy. So you go to 8.3.3 and then do library Metaphor. Is already a meta regression data set in dmeta, which is great. And then you run this code. So you do library Metaphor and then library tidyverse dmeta, and then you look at the meta regression data set. And then you can check for whether or not they are correlated. Multicollinearity, are they correlated? So you can run this code if you want. This is quite advanced, so I don't know if you guys want to actually run it, but if you guys want to, then it's actually quite useful just to understand as a concept. Yeah. So 8.3.1, once you've installed all of this library Metaphor and library tidyverse and all of data metric, you cut and paste this code, then what you can do is just run this simple code and you can see if there's a link. If there's a link, are they correlated? Because in a sense, if they're very, very correlated, then it becomes a problem because you're actually looking at the same variable. So you can see that if you run this code, it will actually give you a chart. You can create a chart, and this shows if there's a correlation. But the correlation is there, but it's mild. It's not great. Yeah, you can see the variables are all over the place. They don't look similar. So reputation is like this triangle, and quality is this up and down, and publication year is like a hat. So it's not really the same. Now this is quite complex code, but just have a go at it, because one of the reasons is because I need you guys to learn how to do newer functions, and this is like an interesting function. Yeah. All right. I'm going to check if you guys have done this. All right, let's do it to you. Kiara, Harjeet, Solongo, Wihan, Rami. Any luck so far? Samavita?
Yeah, I've done up to the chart, but then it says there's no package called performance analytics.
Oh, there's no package called performance analytics. One second. Let me just go back. You then have to try. Let me just see why that episode chart is not appearing. Should be in metaphor. Yeah, it should be in metaphor. So did you load up metaphor, library metaphor?
Yes, yeah, but I'll do it again, see if it's mind.
The other thing is, if it doesn't have the performance analytics, you can probably find it in install packages. You should be able to find it. Oh no, library, because you have to do library. Okay, it's not install performance analytics. I understand. So you have to install performance analytics. Sorry, I should have gone through that step with you guys. Yes, you're right. You're right, actually. So you have to install performance analytics. So you have to find performance analytics. Yeah, you have to find it. So you have to install it. You have to find and install this package. So if you guys go to the install section, it will find it for you. You can search for it on the internet and install it. You can install it. But in essence, this is, to be honest, most of the time when you're doing meta-analysis, you're not going to do this. But this is a check to see if two variables are actually the same variable. Yeah, when we're doing multiple meta regression, we want to say, oh, two variables are not the same variable. Yeah, and then you put up in from your library. Okay, let's go to the room again. Let's go from the bottom. Sumuchuku, Clement, Najwa, Hadi, Muhammad, Kershawn, any luck?
I had some network issues, so I'm trying to run the performance, install the performance analysis now. Thank you.
Eve, Muhammad, Adrija, Giva, Celestine, any luck so far?
Yep. All good.
Oh, good. Oh my God, he managed to do it. Mohammed Basha, Jobran, Faith. Bharat, Maddie, did you manage to sort out your issues?
No, I didn't, which is unfortunately, I think I'm like behind now.
Okay, don't worry. So it's basically 4.2.1.
Yeah, no, I did. I've been to that section and I've redone that bit of like copying and pasting.
Yeah, so you gave your results, yes?
But
Yeah, to MGen.
it comes out with results. That's the issue doesn't come until after I put in m.gen
Yeah, that's fine.
from
So
chapter 8.
So you got your results. You just need to do the meta regression bit.
Yeah, but it just says that m.gen's not found. But I've done the previous steps, so I don't really understand where I've gone wrong.
What did you do? Did you do m.cont?
No, I did m.gen. So I'm trying to scroll back through my code and see. Yeah, it's MetaGen.
MetaGen. Let me have a look quickly. Let me see. So MetaGen sounds correct. MetaGen.
And then the summary, and then
m.gen, yes. Summary m.gen.
Yeah.
Yeah, that's fine. So then it should work, the meta regression. Not understanding if you go to meta regression.
Because then I get the summary and then I put in the years and that also works, but it somehow doesn't work when I put in
The meta
final step.
m.gen.reg, it doesn't work. Oh, it may be that library. Sorry. So you have to do the library. You have to do the library meta. The package.
Oh, okay.
Yeah, you might not
put
have
that in
package.
first.
Yeah, library meta. Try that.
Okay. Thank
and
you.
that might explain it. Okay, because the meta reg is in meta function, and if it's not loaded up in library, it won't work. Okay, let's talk to the others. All right, guys. Harjeet, Kiara, Rami, any luck? It's complicated. Performance analytics. But in essence, it's the same variable, okay? Same variable. And then,
Hello.
yes, any luck?
Please, when I run, I see some error messages under the MV regression data.
Yeah. What error message are you seeing?
Argument 1 does not name a graphical parameter.
In this one, when you read regression data, is it this one, the library performance analytics, and then this one? Because that's a just separate program.
Yes. I get the graph, but in the what do you call it? In the code area, I get some red warning
Red
messages.
warnings. Okay. You can see the graph, so that's fine.
Yes, I can see the graph here.
That's all right. That's more than enough.
Yeah.
Yeah. So I think so. The other thing to note. So that was we basically said, okay, two variables are the same variable. What we can do is that we can now run this with another model. Sorry, with another so quality. So we can just say quality, yeah, and see how much heterogeneity it explains, yeah. And this is we're using another with rather than meta reg, we're using something like RMA. RMA does like these complex multi-regression, but in this for this we're only going to use it for one variable, which is quality, yeah, just quality, and we can see that how much it explains the heterogeneity. Yeah, so we're going to use this RMA, but we're going to just use it on one variable. So this is now 8.3. 8.3. Yeah, 8.3. And then you'll get this. Ta-da! And in this, you will see, just cut and paste this code, guys. And then what you will see is that you will see the heterogeneity is it accounts for 7.37%. Not a lot, but you know. So what I'm trying to say to you is you can use meta reg, which is the easy way to do it. You can use you can check for multicollinearity, which basically means that you're saying two variables the same variable, and then you can run this, which is a single variable, and then they will give you this code. Yeah, and then so if you guys just do this first for now, and then we'll run some more variables, and then it should be fine. I don't know if am I? It is in some ways I'm making it too complicated, but let's see. Sarah, Sumutsku, Rishbash, Clement, Najwa, how are you guys doing so far?
I'm good.
Very good. Hadi, Muhammad, Kershon.
Good evening. I used to call. Hello, I think I have to rewatch the video. Hello?
Sorry? Yes, sorry.
I said I will rewatch the video because I'm watching this thing on the way. Like I can't comprehend anything inside it. So I have to sit down and watch the video. But at the end, I will ask a question. I have a question to ask.
You have a question?
Yes.
What is the question?
And at the end of everything.
Okay, fine. You can ask the end of it. Okay, fine.
Okay.
Eve, Giva, Celestine.
Yep, all good.
Oh, good, very good. All right. So you do another one and heterogeneity. So we're just doing this again and again and again. We're choosing a variable, and last time we used meta reg, but this time we're just using this RMA, and then we're finding heterogeneity. And we can do this one more time. So that was quality, and now we're gonna add in two variables, quality plus reputation. Yeah. So you just cut and paste the next bit of code, and then you should get this. Yeah. So this is the bit of code after this, and then you're basically looking at two. So this is the code with the quality plus reputation, and then you get this. And now you're saying that these two together, they accounted for 66.95% of the heterogeneity. So you explain most of the heterogeneity using these two variables. Yeah, these two variables. Which is easy. Yeah, so everybody can run this code. Then we are going to add in a third variable after that. Kiara, Harjeet, Sulongo, Rami, Monica, any luck?
Yep, all done.
Very good. So, guys, we started with just using a simple variable, which was meta range. Then we said, okay, let's add in some more variables. So we did RMA, and then we did one variable, and then two variables. Laura, any, Zainab, Valerie, any luck?
Yes, I managed to do it. And was I meant to get some graphs with the reputation quality of year? Yeah, good. Thank you.
Halima, Pratik, Rania,
Yeah, all good.
Ayuji, Christel, Najib, Justice, Hamza.
All good, doctor. Thank you.
Very good. You guys are catching up fast. Ali, Khalil, Aki, Nurane, Maddie. Any luck, guys, so far?
I've caught up a bit. I just need to install performance analytics.
That's all right. So just to emphasize again, meta-regression. What is meta-regression? Meta-regression means we're trying to explain heterogeneity. You only use it if there are more than 10 papers and if the heterogeneity is more than 50%. And with meta-regression, what you do is you pick a variable. Oh my God, risk of bias, call it year, date of birth, whatever. You pick a variable. Sorry, diabetes, I mean. You pick a variable and then you say, well, this can explain the heterogeneity and this is great. You have to remember that this doesn't go in the main paper. Most of this goes into the what's called the
Supplementary.
yeah, supplementary. Actually, this is a repeat of the last one. I don't know why I did it twice. Yeah, this is a repeat of the last one. Don't worry about that. And now we're going to run a supermodel, multi-model inference as a piece de resistance. Yeah, we're going to use create a supermodel with 4 predictors: publication year, quality, reputation, content. This is the absolute peak of meta-analysis, meta-regression. You guys are at the absolute peak. Yeah, it's time to climb K2. So cut and paste this code, and you can climb K2 here. Yeah, this is nearly the last bit of code in this chapter, so you should be able to find it quite easily. Yeah, and then it will display this, and it will show, oh my God, publication year is the most important, then content, then reputation, then quality. Yeah, run this bit of code. It is near the end of this chapter. It is, yeah, it should be the last one. Multi-model inference. And it's amazing because it just demonstrates the model for you. Yeah. It's very, very useful because it's very useful because it just gives you the answer in one go. All right. Let's see who's been able to run this. Kiara, Harjeet, Sulongo, Rami, anybody be
Yes,
able to?
yeah.
All good?
Yes,
Yeah,
yeah.
all good.
Samavi, Monica, Gunayat, Laura, you're I can't on YouTube, but you have been able to do this, yes? Are you doing this?
Sorry? No, I did. I've been through every session except the second one, which I caught up.
Okay, perfect. You've been able to do this bit of code, yeah?
Yep.
Very good. Zainab, Valerie, Halima, Pratik, Rania, yes? All good? Christelle, Najib, Justice? Hamza, Ali Khalil, Aki? Good? Okay. Nurane, Bharat, Faith,
Yeah, all good.
Jobran, Mahmood, Celestine, Geva, yes?
Yes.
Eve, Gershon, Muhammad, Hadi, Najwa, yes? Okay. Clement, Rishpash, Sumuchku,
I'm
yes?
good to go. I'm okay. I've
Sola,
done it.
Adrija, Muhammad, sorry, Murad, Muhammad Murad, Yes? Okay. So let's go through this again from the beginning. Okay, meta regression. Meta regression means, oh, I've got fixed effects, which means there's a fixed variation. Grape versus grape. Random effects. There's some olives in there. Meta regression. Wait, I've got the answers. I've got the answers. I know why this variation is occurring. So it's a third variable on top. So that becomes this formula, which is fixed effects plus random effects plus my model. Yeah. And then obviously, this was the as a standardized mean deviation one we ran, which is meta gen. And then we used a hedges, which was for the continuous variable. And then we use REML for the heterogeneity. And HAKN is the Hartung Hartung effects, which are basically just like a filter. And then this gave us this, yeah? Hedges, which is the inverse variance, and REML for the heterogeneity. Which estimator do you use for heterogeneity? For continuous data, you use the RMLE, and for binary, use the Paul-Mendel. To keep it simple. Again, fixed effects is the first one, and then random effects is the second one, and then we plug in a third formula. Yeah, hedges we talked about. Yeah, hedges is the one which is default for inverse variance for basically for continuous data. And then we did this. Oh my God, what is this? Year. So we put a variable. Then we ran the most simplest variable, which is meta reg. Yeah. The meta reg basically said, oh, 70% of the heterogeneity is 77% heterogeneity is from the year. So this was the most simple form of meta regression. And to be honest, for the most part, for most papers, that's more than enough. You can run this on 3 or 4 variables and you see, and you don't have to use a big model. And then you generate a nice bubble plot, which you stuff into supplementary table and you're done. Yeah. But, and then we can do it on something else. Look, meta reg on risk of bias. And then it gave you a whatever. But then we can do multiple meta regression because we're crazy. And it's like, oh my God, let's create a fancy model. Although we don't want to take the risk of overfitting, which is like this green bit, which means that, which is ridiculous. To multicollinearity basically meant that two of the variables are the same variable. Yeah. And then for meta regression, you used to use force entry. We put all the predictors in simultaneously. But in this case, we're going to do it gently. And then we go library metaphor. We run the meta regression data. We first check for multicollinearity. Are they the same? So this shows us this chart, and it says, well, they're all a bit different. There's some linkage, but not huge. And then we put in the first, which is quality. And it says that explains about 7% of the heterogeneity. Then we say quality plus reputation, and then that explains the 66.95% heterogeneity. We're getting somewhere. And then what we do is then we say, let's put them all in together. Publication year, quality, reputation, continent, the whole thing. And we find that yes, it does explain a lot of the heterogeneity, but these are actually interesting enough. It doesn't give you the heterogeneity percentage. It gives you ranks the 5 best models because this actually uses AI and gives you all these different models. And what it's saying is that these are the top models that work. Yeah, the top models that work. And in these models, it says publication year is probably the most important predictor, then continent, then reputation, then quality. But the problem is that this you can't really put in a journal easily, or at least in this form, easily. I mean, you don't tend to see this in journals. What you see is the bubble plot, and you see the simple meta regression. But the reason I've gone into this more detailed stuff is you have to remember it's a moving target. If you're going to publish, you need to be, familiar with the more advanced statistical techniques because somebody else will have a paper and it'll just be a bit simpler, and you need to know the latest stuff. Okay. And now let's torture everybody one last time before we stop. Chiara, Harjeet, Solongo, Rami, any questions?
No, thank you very much.
No questions, thank you.
All right. Samavita, Monica, Buyant, Zainab, Valerie, any questions? No? Halima, Pratik, Rania, Irji,
No
Chris-
question.
No? Justice, Hamza, Ali Khalil, Aki, any questions? Nurane, Maddie, any questions? No? Faith, Muhammad Nahuli, Celestine, any questions?
No questions. Thank you.
Okay, fine. Do you guys feel like you could do a meta-analysis yourself now? Beginning to end? What do you guys think? Yes, no?
To some extent, yes.
Very good. That's the whole point. The point is that you should be able to do all of this without depending on anybody. The idea behind this course is to make you completely independent. That, there obviously will always be some minor questions, but you can read them yourself so you understand the basic principles. Yeah. Oh, Clement has got a question. Clement. Clement, do you have a question? You have to unmute yourself to ask the question. Oh, Clement's not asking the question.
Okay.
No.
Hello.
Yes, sorry. Yeah?
Some of us don't have access to current database. We only have access to PubMed. So can we use it to extract our data?
You have to extract your data, Clement, from the. So this is how I do it. Most of the topics I do, there's always a meta-analysis in place, yeah? So I don't need to reinvent the wheel. I look at the newer papers. I look at the data in the older meta-analysis. I look at what the analysis have done. And some of the data I just extract out the old meta-analysis after double checking it from the older papers. And then I added 2 or 3 new papers. And then I rerun and create forest plots first. Yeah. And then I create my get somebody else to create my demographics table, which is like, what about the studies? And then somebody else to do the screening and see if any new papers come up. And then somebody else write the intro, somebody else write the discussion. That way, the whole paper is finished within 6 weeks to 2 months. But the first bit, generating the new forest plots, I do with one person, and that person and me, we do it sort of together over like a month or 2. Oh, sorry, a few weeks. That's a critical aspect of it. Every other task is easy, yeah, and anybody else can do it. But this bit, the analysis itself, you need to do. Okay? All right, let's ask everybody. Any other questions? Okay.
Yeah,
Just-
so for the
Yeah.
meta regression, like, how do you choose like what factors you want to do the regression?
Oh, it's
for?
just the data that's present in the papers. So the papers will have some demographics data. They'll have like age, or they'll have sex, or they'll have things like that. You just use that generally.
Okay, that makes sense. Thank you.
Okay, let's torture some more people. Zaina, Bharat, Adrija, Sola, any questions?
All good.
Samuchku, Rishpash, Claire, oh, the Clement we already spoke to. Najwa, Hadi, any questions? Krishan, Eve, Celestine, Muhammad Nahuli,
No questions.
Faith, Madi, Nurane, any questions? Aki, Ali Khalil, Hamza, Justice, Najib, any questions? Kristal, Ayurji, Rania, Pratik, any questions?
No.
Okay, very good. All right. Fine. In that case, we've got it's 7 o'clock, so we're gonna end the session here. Let me just say. Oh, I'll do a quick poll, guys. What topic do you guys want next time? Do you guys want? We could do actually. We can do. What's it called? Publication bias, subgroup analysis. We can do, yeah, or do you just, or we could just do general meta-analysis. We could just try the other types of summary measures. What do you guys want to do? Publication and funnel plot. Okay. What about the others? Yeah, sorry.
Our email contains forest plots that we're going to do for forest plots today.
Sorry?
On the mail. The email I received contained that we're going to do forest
forest plots. Okay, let's do
and,
more forest plots then next time. Fine. We can do some of the other measures. And what I'll do is at the end of it, I'll do some publication bias and funnel plots. But I think the thing is you guys are finding normal meta-analysis quite quick now. So I have to do something else. You guys are finding it easy. All right, that's fine. What we'll do is I'll do it next time. I think we might do some other summary measures, and then we'll do some publication bias and funnel plots. Yeah, that's fine. That should be reasonable. Okay.